afternoon, students. Today we are going to discuss about Banker's algorithm for avoiding deadlocks. First of all, what do you mean by deadlock? A process in a multi-programming system is said to be in a state of deadlock if it is waiting for a particular event that will not occur. When a process requests resources, if the resources are not available at that time, the process enter into a wait state. At the same time, the requested resources may be held by some other waiting process. So, both the processes are permanently blocked. This situation is called deadlock or deadlock. Consider a system with one tape drive and one plotter process. P1 requests the tape drive and process P2 requests the plotter. Both the request is granted. Now, if P1 requests the plotter without releasing the tape drive and P2 requests the tape drive without releasing plotter, this makes none of the process to proceed. This is the situation of deadlock. Then what are the characteristics of deadlock? Necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, circular wait. Only mutual exclusion, only one process at a time can use the resource. If any other process requests the same resource, the requesting process must be delayed until the resource has been released. Hold and wait, there must be exist a process holding at least one resource and is waiting to occur an additional resource that is currently being held by another process. More preemption, the resources cannot be preempted, that is, they cannot be released until the completion of task. Circular wait, there must exist a set of waiting process P0 to Pn. P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. Pn minus 1 is waiting for a resource that is held by Pn. And Pn is waiting for a resource that is held by P0. Then introduction to the Banker's algorithm for avoiding deadlocks. The Banker's algorithm is a crucial concept in the field of computer science, specifically in the management of system resources and the prevention of deadlocks. This algorithm developed by Digitchetra provides a systematic approach to ensuring the safe allocation of resources to processes, thereby avoiding the potential for deadlocks to occur. By understanding the principles of the Banker's algorithm, computer system can be designed and implemented with enhanced efficiency, reliability, and security. Understanding resource allocation and deadlocks, we must familiar in resource allocation graph. Deadlocks can be described more precisely in terms of directed graph called system resource allocation graph. The resource allocation graph consists of vertex P, vertex R. P stands for active process in the system. Vertex V R that contains all the resources in the system. Edge Pi to Rj called the request edge. Rj to Pi is called the assignment edge. This is the way we are going to represent the resource allocation in deadlocks. Resource allocation in a computer system, resources such as CPU time, memory, and I/O devices are often shared among multiple processes. Efficient resource allocation is crucial to ensure that all processes have the necessary resources to complete their task without interfering with one another. The deadlock occurs when two or more processes are waiting for resources that are held by other process, creating a circular dependency. This can lead to a situation where no process can make progress ultimately, resulting in a system-wide stall. Importance of deadlock prevention. Deadlocks can have severe consequences, including system crashes, data loss, and reduced overall system performance. Preventing deadlock is therefore a critical aspect of computer system design and management. Defining the Banker's algorithm. resource allocation model, process requirements, safe state, dynamic resource allocation. The Banker's algorithm is based on a resource allocation model where a finite number of resources are shared among a set of processes. Each process has a maximum resource requirement, and the algorithm ensures that the total resource requirements of all processes do not exceed the available resources. Safe state. The algorithm maintains a safe state by ensuring that at least one process can always be executed without causing a deadlock, even if all other processes request their maximum resource requirements. Dynamic resource allocation. The algorithm dynamically allocates resources to processes based on their current needs and the available resources while maintaining the safe state. Necessary conditions for deadlock already we discussed. Resource allocation and request handling. Initial resource allocation. The Banker's algorithm begins by assigning a fixed number of resources to each process based on their maximum resource requirements. Resource release handling. When a process releases a resource, the algorithm updates the available resources and checks if any waiting process can now be granted their request, thereby maintaining the safe state. Resource request handling. When a process requests additional resources, the algorithm checks if granting the request would lead to an unsafe state. If not, the request is granted. Otherwise, the process is made to wait until the resources become available. Safe state and unsafe state. A safe state is a resource allocation state in which there exists a sequence of processes that can be executed without causing a deadlock, even if all processes request their maximum resource requirements. Unsafe state. An unsafe state is a resource allocation state in which there is no sequence of processes that can be executed without causing a deadlock, even if all processes request their maximum resource requirements. Avoiding unsafe state. The Banker's algorithm is designed to avoid unsafe states by carefully managing resource allocation and ensuring that the system remains in a safe state at all times. Detecting unsafe states. The algorithm uses a mathematical analysis to determine whether a given resource allocation state is safe or unsafe based on the available resources and the maximum resource requirements of each process. Implementing the Banker's algorithm. Resource allocation matrix, maximum resource requirements, available resources, safety check. The algorithm maintains a resource allocation matrix that tracks the current allocation of resources to each process. Maximum resource requirements algorithm also maintains a record of the maximum resource requirements for each process, which is used to determine the safe state. Available resources. The algorithm keeps track of available resources, which are the resources that are not currently allocated to any process. Safety check. The algorithm performs a safety check to ensure that granting a resource request will not lead to an unsafe state before actually allocating the resources. Advantages of Banker's algorithm. Deadlock prevention. The Banker's algorithm effectively prevents deadlocks by ensuring that the system remains in a safe state at all times, even as resources are allocated and released. Resource utilization. By dynamically allocating resources based on current needs, the algorithm maximizes resource utilization and overall system efficiency. System stability. The Banker's algorithm promotes system stability by maintaining safe state, which ensures that the system can continue to operate without interruption. Limitations and considerations. Overhead, complexity, assumptions. Implementing the Banker's algorithm can introduce some computational overhead as it requires constant monitoring and analysis of the resource allocation state to ensure safety. The algorithm can become complex as the number of processes and resources increases, making it challenging to implement and maintain in large scale systems. The banker's algorithm relies on certain assumptions such as the ability to accurately estimate the maximum resource requirements of each process, which may not always be possible in real world. Conclusion and key takeaways: deadlock prevention, dynamic resource management, versatility and limitations, ongoing advancements. Understanding resource allocation, resources, allocations, and deadlock. Proactive approach, resource management, and dynamic evaluation for introducing the banker's algorithm. It is a proactive solution for deadlock avoidance. It determines safe resource allocation to prevent deadlocks before they occur. The algorithm continuously evaluates the system state to ensure safety. Step-by-step explanation about the banker's algorithm. Resource request. Process request additional resources from the system. Safety check. Algorithm evaluates if granting the request would lead to a safe state. Resource allocation. If safe state, the resources are allocated to the requesting process. Handling resource request. Algorithm tracks the resources currently available in the system. Request evaluation determines if granting the request would exceed the available resources. Allocation decision: if safe, the resources are allocated, otherwise, the request is denied. Determining safe state, resource availability. Algorithm checks if the system has enough resources to satisfy all processes. State exploration, evaluate possible sequences of resource allocation to reach a safe state. Safe state confirmation. If a safe state is found, the resource request is granted, otherwise it is denied. Allocating resources safely, collaboration. The algorithm facilitates cooperation between process. Protection. It safeguards the system against deadlocks and resource starvation. The algorithm adapts to changes in resource availability and demand. Real-time setup. System resources. A computer system has a finite set of resources: CPU, memory, storage. Active processes. Multiple processes are running and requesting resources dynamically. The algorithm will be used to manage resource allocation and avoid deadlocks. Applying the banker's algorithm, consider process P1, P2, P3, request 322, P2 for process, request is 613, request is P3, 422, allocated 110, 613, 211, available resources 333, 122. Now apply the safety algorithm and resource request algorithm. The safety algorithm will find out whether a system in a safe state or not. It is as follows. Let work and finish be vectors of length m and n respectively. Initialize work is equal to available and finish of I is equal to false for I is equal to 1 to n. Find an I such that both finish of I is equal to false, need less than or equal to work. If no such I exists, go to step 4. Work is equal to work plus allocation, finish of I is equal to true. Go to step 2. If finish of I is equal to true for all I, then the system is in a safe state. The algorithm may require an order of m by n operation to decide whether a safe state is safe. Resource request algorithm. Let request be the request vector for process Pi. If request of j is equal to k, then process Pi wants k instances of resource type or j. When a request for resources is made by processes Pi, the following actions are taken. If request of I less than or equal to need of I, go to step 2. Otherwise, an error exceeded maximum claim. If request of I less than or equal to available, go to step 3. Otherwise, process of I must wait since resources are not available. have the system pretend to have allocated the requested resources to process PI by modifying the state as follows. Available is equal to available minus request. Allocation is equal to allocation plus request. Need of I is equal to need of I minus request of I. If the resulting resource allocation state is safe, the transaction is completed and PI is allocated its resources. Key takeaways: proactive deadlock avoidance. The Banker's algorithm continuously evaluates system state to prevent deadlocks. Dynamic resource management. It adapts to changing resource availability and demand to ensure safety. Collaborative decision making. The algorithm facilitates cooperation between processes for optimal resource utilization. Thank you for your cooperation. Thank you for watching.